afternoon, everyone. Today we'll be discussing and solving some questions related to week 10 content of control engineering course. So, week 10 content basically includes determination of transfer function. We can say experimental determination of transfer function and effect of right half plane zero on the system response. So, you must have gone through the course means through the week 10 content. So we'll discuss a little about that and then we'll start with few problems. So basically in week 10, we have seen that if there is a system G, and there's some input given to this system, U of t, and you have to find y of t. So generally when we have some input is given to system, some output like behavior of system has to be determined. In that case, what we had studied earlier, that we'll have some basic physical law like KVL or Newton's law of motion. Like this law we apply and try to find the dynamics of the system. This is kind of physical modeling. And another was this experimental modeling, in which what is done that since this is a linear time invariant system, we are dealing with linear time invariant system. So for this, we know that if we know the impulse response of this system, we can find the response from the system generally. So that is in terms of time domain, and in terms of frequency also, what we say that if sinusoidal input is applied, output is same sinusoidal input of same frequency but with different amplitude and phase shift. So if we can apply sinusoids sin omega t plus phi or sin omega t, we can say for different frequencies. Omega is the varying quantity. Now there should be some response in the output. So in y output we'll get some a sin omega t plus phi for different frequencies. So at different frequency we'll have some different a value, which is again because here the amplitude is 1, and there will be some phase which is omega. This you have k, and we'll have some phase shift. It may be some kind of delay. So if signal is applied, sinusoidal signal with varying frequency, we can find the response of the system to different frequency, and from this response we can have this Bode plot, and from Bode plot we can find out what is the transfer function of the system. Now once we get the transfer function, we know that LTI system can be represented by transfer function. It's characterized by basically transfer function. So once transfer function is known, output to all the inputs is known. So this is one way of determining the dynamics of a system. So this is what has been discussed in week 10. And apart from this, we saw the effect of right half plane zero. So up to now, the system that we have studied is a stable system. So suppose system s plus 2, s square plus 3s plus 1. Input is provided to the system ut, and you get some output yt. Now this is a system, and this is a second order system with poles in left half plane. Now this we have studied. So it has 1 0, that is is equal to -2. So we can, let us see the root locus of this one. So we have this system. ZPK. What is the root of numerator? -2. Root of denominator. Okay. We don't have root relational equation, so we'll use transfer function. And this is 1, 2, s plus 2, s square plus 3s plus 1. This is the system. So we have two rows. We obtain this root locus. This is one pole. This one is another pole, and this is the 0 for that system. Okay, so we can see the root locus. I mean, for if we plot the root locus, all the poles are in left half plane. Anyway, the open loop poles are also in left half plane, so this system is stable. Now for this open loop system, this much we know. So because of this 0, that is at -2, suppose this is this. So we can have this as cascade. We can visualize it like this. So this UT, this one. So basically this is derivative of UT plus 2U, U dash. And then Y is Y d2 Y by dt square plus 3 dy by dt plus Y is equal to du by dt plus 2U. So if this is input, suppose there is this step in standard signal, which is a step input. So if there is this step input which is given to the system, this having this dynamics, then this also has an effect, this derivative. So this is kind of positive, and response is basically kind of fast, and we see some kind of peak overshoot in this. So this is the effect of left half plane 0, and this we have seen in earlier lecture also. Now when we have this as, suppose we have do like zeros in right half plane. So now the transfer function suppose is minus s equals to s square plus 3s plus 1. This is the transfer function. Here we have a root in root, or we can say zeros, root of the numerator or 0 of this transfer function in right half plane. So in this case, if there is this input which is step input, then we see a undershoot initially. What we see is the undershoot initially and then system reaches this one. So this is not kind of a behavior that we want because we want the error to be minimized to this step response, like tracking. So this is one thing that is present in the system having right half plane 0. So this type of system is called non-minimum phase system. So this is when there is 1 0. If there are two zeros, we'll have this kind of zero crossing like this. It depends on number of zeros in right half plane. So basically this type of behavior is present in this non-minimum phase system. So this is non-minimum phase system, and the system that we have been dealing up to now is minimum phase system. So for this minimum phase system, this border plot, this whole amplitude and this phase are uniquely related. But for non-minimum phase system, we can have same amplitude but with different phase response. So let us analyze few cases. Now we had these three systems. So let us say we have this one. This is one system we have. And there is another system in which we have some delay. So this is tau. And we have another system which has 0 in right half plane. So minus s plus 4. So we'll just see the behavior of this system. Just see this one. So we have system which is pk 4 minus 4 comma minus 2 minus 3 comma again equal to 1. Okay, so this is the first system, and then we have system with delay. This is yeah, 1 4 comma convolution of 1 s plus 2 and s plus 3 comma put delay. What is the delay? Yes, 1 second. So this is another system. Now we have these two systems. So let us see response of these two to a step input. input is a step, and this system, if you can see, that one with left half plane 0 is this blue curve, and it is reaching 0.7. So this is not tracking the system, like not tracking the input. There is some error, but it is reaching some steady state. And for this system, if we see with delay, so it has 0 response up to 1 second, and after that it has started responding to the input. So that means we have some time delay. Now this time delay is basically means that in if we see frequency response, there will be delay in the delay introduced in the Bode plot. So whatever Bode plot we have for this system, this blue one, which is the minimum phase system, this another system will have same magnitude plot, but the phase plot will have more delay, and therefore if it has more delay, that means what? Means the phase margin will be decreasing. The system is relatively less stable compared to the system with left half plane 0. So let us see Bode plot also. Mm. Okay, some of the frequency part is from, it's from 0 to something. Now this one, this blue one, what is expected since it has 1 0 in left half plane and 2 poles. So the phase angle at omega tending to infinity should be minus 90. Number of poles, that is 2 minus 1. So that should be approximately minus 90. So it should reach minus 90 degree. And for this one, this is not a minimum phase system. So we'll see there is some delay that we have verified through this step response. So you can see this one, this blue plot is reaching minus 90 degree as time, like as the frequency is increasing from 0 to minus 90. But this red one, it also has having the same magnitude plot, but it delay is increasing with frequency. Now let us see what is the stability margins. Okay, so here we are getting the gain margin. Now this system has to be need to have some gain so that it has greater than 0 dB gain, and then only we can see what is the phase margin. But if we increase again, let us say increase again and see what is the This one, you can see the page margin is 96.1, but this one is having negative page margin. So basically this one is already unstable. We have increased gain up to more than what is required for bringing it to verge of instability. So basically, what is the thing that from step response, we got to know that, okay, this system is behaving in some way, and for this system, there is some delay, and then system is being. Now, for this system, which is having right half plane 0. So, how do we know that? How can we characterize this? Okay, so for this one, minus s plus 4. So, there is a system minus s plus 4 by s plus 4. S plus 3. If we see the root locus or the pole plot, so not the root locus, basically pole plot. So we have 1, 0 at minus 4, sorry, 4, and then we have two poles at minus 2 and minus 3. Okay, so what can we say? For this one, minus 2, we have minus 3. If we place a pole and 0, both at minus 4, so this is basically cancelling out. And now this is for analysis purpose. We are not going to place any mole and 0 at this minus 4. We're just trying to analyze as of now. So now this, we can say that there are two systems in cascade with 0 at minus 4 and pole at minus 4. And another system which is having pole at minus 2, minus 3 and 1, 0 at minus 4. Signal system. So this is the same axis for all the. So this system, so for this system, what we can write, this is s plus 4 by s plus 2, s plus 3. And then we have minus s plus 4 by s plus 4. These are the cascade. So this one, we know this is a minimum phase system. And this one, if we see this one, and if we try to find the magnitude plot of this transfer function, so this is kind of all pass filter. We'll just see why. And therefore, if we plot have the frequency response, or we can say border plot for this system, so it will have same magnitude plot as this one. Suppose the magnitude plot is like this. This is the phase plot, this is magnitude plot. So for this system, This will be 180-degree shifted. Now, since this angle is increasing, the shift angle, so basically phase margin is decreasing for this system. So why it is 180-degree shifted? So we have this transfer function. This is the all pass filter transfer function. Now if we have this frequency response analysis, we'll just try to find out what is the amplitude. Amplitude is 16 minus omega square. And the phase is all classes. And 16 plus omega square by 16 plus this is 1. And what is the phase? This is minus tan inverse omega by 4 and minus tan inverse omega by 4. This is because of pole and this whole is because of 0. Minus 2 tan inverse omega by 4. If we plot the amplitude, amplitude is simply 1 for all frequency. And this phase is what for 0? It's 0 degree. So this is 0. And for infinity, it's like minus 2 tan inverse infinity. So it's 90 degree minus 2. And this goes to minus 180 degree. Okay. So that means if we have this system in cascade, this all pass filter, basically why this is all pass filter? Because it is passing all frequencies. So there is no attenuation. Otherwise, we would have, if we had this type of system, this type of magnitude response, then we say, okay, it is allowing frequency up to 3 dB, up to which it crosses 3 dB. So we have this low pass filter. It is passing low frequency with some amplification or with like buffering, but it is attenuating other signals which is of high frequency. But here it is not attenuating any signal, it is passing all the signals, so it is a all pass filter. So it's basically means there is no effect on gain if it is cascaded with another system, but there will only be a phase shift which is approx 180 degree at infinity frequency, means infinite frequency or higher frequency. So because of this, when we are saying that this system will have Rebode plot which has similar magnitude plot as this one, but phase shifted 180 degree with respect to its phase plot. So this is with this right half plane 0, but we have this delay. Now when we are adding right half 0, right half plane 0, so basically it's kind of, we are approximating this delay with right half plane 0 because we want a rational transfer function, so we are just trying to approximate. So for this we do pad approximation of this one. So if we have this e to minus tau s. So we know that we can have transfer function or rational transfer function. Either it would be strictly proper or proper. So number of poles would be greater than equal to number of zeros. Now for e to the minus tau s, what we can write? If we have, we can write this as 1. If we have e to the power x, so we can write 1 plus x square by 2, an infinite series like this. And we say that first term, this first delay is prominent. So we have e to the minus tau s. Now this approximation is not physically realizable. So we do a, how can we write this? We can write this as now this will be the minus tau by 2s and this would go in numerator, so it will be, so how do I write it? 1 minus tau by 2s and 1 plus tau by 2s. Okay. So this is the approximation for this one. Now let us approximate this system, which is the delayed system. Is e to the power minus s plus 4 by s plus 2, s plus 3. So this is e to the power minus s plus 4, s plus 2, plus 3. Now we'll just replace this by approximation. So the cell will be 2.5s, and then so what do we get? This is a system, like approximated system. So if we just take it out this 0.5 outside, so this will be 2 minus s. S plus 4, and then we have s plus 2, s plus 3. Now this is a non-minimum phase system because it has 1 0 at 2. So we'll see if we plot the response for this system, we'll see some kind of undershoot initially because it has one number of zeros equal to 1, and then this is steady state response. So basically, if there is a delay in system, that delay we can approximate it using this data approximation, and then we'll having this non-minimum phase system, and we can then try to analyze that one also. So these are some few things. Now let us proceed to next part. So this is one question. It says that this is the minimum phase Bode plot. So that means all the poles and zeros are in belongs to left half as plane. Okay. And this blue dashed one is the actual plot, border plot. This is the magnitude plot, and this one is the space plot. And for experimental determination, we had seen that if we have been given this border plot through some experiment and all, obtained through some experiment. So from that, what we do, we draw asymptotes to that one, to that plot, and then we try to find out what is the transfer function of that one. So from this one, let us see. So these are the asymptotes, and we have to find number of poles in the system. So if we see initially, slope is minus 20 dB per decade, because this is 40 dB, this is 20 dB, here it is 20 dB, and what is the, this is 0.1 and this is 1. So 1 by 0.1 is 10. So this is a decade. And in 1 decade, it has decreased from 40 dB to 20 dB. So it's minus 20 dB per decade. So since the initial slope is minus 20 dB per decade, that means there is a pole at origin. This much we know. So it's a type 1 system. How do we get to know? Initial slope is of magnitude plot is minus 20 dB per decade. Okay, this we know. So there is a term in denominator which is S. Now, if we see at omega equal to 1 radian per second, omega equal to 10, it is like this. So the plot is just having no slope, so it's 0 dB per decade. That means the slope has changed, like increased. So what does this mean? That there must be a zero at that point, because it has changed the slope of the border plot, border magnitude plot, from minus 20 dB to 0 dB per decade. And at this point, which is 10 radian per second, here again it has started decreasing. Slope is negative. Let us see. This is 110. So this is 1 decade again. And in this decade, here it is 20 dB, and at this point it is 0 dB. So this is total 20 dB decrease. So again, this is minus 20 dB per decade. So that means here there must be a pole. Same we can see from here also initially, because here there is a 0. So page is like this, and so anyway, from this one we are getting this point. So from here what we can see, at omega equal to 0, we have one pole, and then at omega equal to 1 radian per second, we have one 0 here, and omega equal to 10, we have one pole. And omega equal to 10 radian per second, we have one pole. So as of now, at least we can say this is a type 1. So we have 1 by S. Suppose this is gain K, which we don't know. So this is S, and then we have 1 0 at 1 radian per second. So this is 1 plus omega is. So this is 1 by tau. So this will be tau S. So this is 1 into S, and this is 1 plus S by 10. What is this? K 1 plus S by S 1 plus 0.1 S. This is a basic structure of this transfer function for which the Bode plot is given. Okay. So how many poles are there? We have 1 at 0, 1 at 10. So this is 2. Now let us proceed to next question. So number of zeros. So this also we found out. There is 1 0 at omega equal to 1 radian per second. So this is 1. Now it says velocity error constant of system. So obviously we know this is a type 1 system. K 1 plus S by S. This is the transfer function. Now for this transfer function, we have to find the velocity error constant. So initially, if we see this one, this for low frequency, what we can see is we can say that the magnitude is 20 log K by just omega. This is for low frequency. Now for this one, what we can see? So this 20 log K by omega, this is its value is 40 dB when omega is 0.1. So let us say, so this is 40 dB when omega is 0.1. So we'll just have this one. This is K by 0.1. And this will be 10 to the power 2 equal to 40 by 20. So this is 100 and K will be 10. This is kV also. kV. So what do we get? kV equal to 10. So what is the transfer function? It is 10, 1 plus S by S, 1 plus 0.1 S. Okay. Now it is saying that for a minimum phase system, with 2 zeros and 4 poles. So number of poles is equal to 4. Number of zeros is equal to 2. The slope of log magnitude curve at omega equal to infinity. So at infinite frequency, we know what would be the slope. Slope will simply be slope of log magnitude curve. What this should be? This should be 20 dB per decade multiplied by number of zeros minus number of poles. So this is 20 into 2 minus 4, which is minus 40 dB per decade. This is what we know. And for phase angle, also we know that this is for magnitude log, or we can say log magnitude because we are dealing with in dB. Another one for phase plot for non-minimum phase system, we can say slope is 90 degree, which is multiplied by number of zeros minus number of poles. Okay. For a non-minimum phase system with 2 zeros and 4 poles. So same number of poles and zeros, not exactly same value, but same number of poles and zeros. And we have to find the log magnitude curve slope at omega equal to minus infinity. Sorry, is equal to infinity. So for high frequency. So for this, it is will be same because this is non-minimum phase system. What is the gain contributed by non-minimum phase system? Means we had seen that any non-minimum phase system, this is a non-minimum phase system. And for this system, what we can say, this is a cascade of a minimum phase system and a all pass filter. So whatever magnitude this is having, it will be same as the magnitude of this one multiplied by this, or if we say in terms of dB, so magnitude of this one plus magnitude of this one. This will be 20 log this minimum phase magnitude plus 20 log this all pass filter magnitude. And all pass filter magnitude is 1 that we have seen. This is 1. So this will be 0. So magnitude is what? Same as this minimum phase system. So that means slope will be same as number of zeros minus number of poles. And this will be minus 40 dB per decade. Now if we see, for a minimum phase system with 2 zeros and 4 poles, the phase angle degree at omega equal to infinity is, so this is a minimum phase system with 2 zeros and 4 poles. So what do we expect? We have just now we had seen that, okay, there was one mistake that I did. It's not slope, it's angle. To what angle it is reaching. Phase angle. So what do we have? This phase angle is equal to 90 degree into number of zeros minus number of poles. Let me erase this one. Number of zeros minus number of poles. What is the number of zero? That is 2 minus number of poles is 4. So it's 90 degree into minus 2, and this is minus 180 degree. Okay. Now this is a phase angle of minimum phase. For non-minimum phase, So now it depends how much delay is being introduced. Based on that, this phase angle will change, and phase angle will be greater than minus 180 degree because there will be additional delay, so obviously. So if we say that for non-minimum phase system, the two zeros, one zero is in right half plane and left half plane. So for one zero, the effect will be considered. And if there are two zeros in right half plane, then for two zeros, the effect will be considered. So if there is one zero in right half plane, so that means additional 180-degree delay will be there. And if both the two zeros are in right half plane, so additional 360-degree phase delay will be there for non-minimum phase system. So that's what it is like. Okay. So this is the next question. It says derive the transfer function of magnitude asymptotic Bode plot. So this is approximated plot, that is from actual Bode plot, and transfer function has to be derived. Once transfer function is derived, we need to find the phase margin of the system. Okay. So what do we know from this system, like from this Bode plot? Initially, the Bode plot, magnitude plot is constant. So that means this is a type 0 system. And for this one, the initial value will be, if the system is GS equal to, since this is type 1, so we can say S plus A, S plus B, or some term in, but in there is no S plus A dash, S plus B dash, but no S to the power 0. So there is no pole at origin. Now for this one, for low frequency, we can say that magnitude is 20 log K. So what is the magnitude here in this Bode plot? It's 18.1. So 20 log K is 18.1. If you solve this logarithmic gamma, you'll get K equal to 8. Right. So this we know, K. K is done. Now let us find this poles and zeros. So at omega equal to 0, or sorry, this is 1. 10 to the power 0 is 1. At omega equal to 1 to omega equal to 2. It is having minus 20 dB per decade. So this slope has changed to minus 20 dB. Earlier it was 0 dB per decade. So since slope has changed in between 1 radian per second to 20, that means there is a pole here. And then radian per second to slope is minus 20 dB per decade. This implies pole at omega equal to 1 radian per second. Now, for omega equal to 2 to omega equal to 3 radian per second, again the slope has changed and it has decreased by minus 20 dB per decade. So it's now 40 dB per decade. That means again there is a pole at this location. So between omega equal to 2 radian per second and slope is minus 40 dB per decade. So slope has decreased. And this implies pole at omega equal to 2 radian per second. From there again there is a pole here, and from 4 the slope is minus 40 degrees. So it has increased by 20 degrees. That means there is a 0 here. Between omega equal to 3 radian per second and 4 radian per second, it's minus 60 dB per decade. And there is a pole at omega equal to 3 radian per second. And apart from this, last we saw 4 radian per second and infinity, it's minus 40 dB per decade. So there is a 0 at omega equal to 4 radian per second. So this we can write 1 by tau 1, 1 by tau 2, 1 by tau 3, 1 by tau 4. What we have. The transfer function now can find. We had this gain k, which is 8. And then we have 1 0 at omega equal to 4 radian per second. So it's 1 plus tau s. So tau is 1 by 4. We can say tau 3. Just tau 4. Okay. And then we have 1 plus tau 1 s, 1 plus tau 2 s, 1 plus tau 3 s. So this will be 8, 1 plus 1 by 4 s, 1 plus s. So this will be 12. First write this one, then simplify this. So we have 8, 1 plus 1.25 s, 1 plus s, 0.33 s. Okay, we can write in whole zero form. So this will be 12 s plus 4, s plus 1, s plus 2, s plus 3. So this is the transfer function. Now we can find the gain like phase margin. So we know phase margin for this one, the G of j omega magnitude should be 1. So from there we can find omega gc, gain crossover frequency, and we'll try to find the phase margin. So we can find the phase angle of G of j omega at omega equal to omega GCF, and we can then again find from minus 180 degree how much far it is. So that would be the phase margin. So we'll not do the calculation because we have already done this calculation in earlier sessions. So we'll just see it through the MATLAB plot. Let us see what is the phase margin. So we have system which is ZPK. This is 4, 1, comma 2, comma 3, comma 12. Oh, sorry. The right option. That's the next question. Okay. We have this border plot. So what is the phase margin? It's 38.8 degree, and at what frequency is that? 4 radian per second. Okay. What is the magnitude here at 4 radian per second? Approximately 0 degree. So this is asymptotic plot. So we are trying to find more accurate plot, and here at 3.39 radian per second, phase margin is 38.8 degree. So somewhat here. This is 4, this is 3, so in between this one, there is some value. Okay. So what is the phase margin we have found? This is 38.8 degree. Now it is being said that cascade the above derived transfer function with another transfer function which is T1s equal to s minus s plus 4. Okay. The open loop steady state response to unit step. So the transfer function that we have found is 12 s plus 4 plus 1 s plus 2 s plus 3. And now the new transfer function of the system is s plus 4 s plus 1 s plus 2 s plus 3. The system is stable because both are in right half plane. Now it has 1 0 which is in, and both are in left half plane, and it has 1 0 which is in right half plane. So this is kind of a non-minimum phase system. Now we have to find the steady state response to unit step. I'll simply apply this one. Limit s tending to 0. S into ys. What is ys? As ys is a step input multiplied by this transfer function. So this is 12 s plus 4 minus s plus 4 s plus 1 s plus 2 s plus 3. This will cancel out. We have 12 into 4 into 4. This is 32. So with same C1, system has right half 0. Okay, this we know. So it experienced and understood. The absolute value of peak understood is. So we'll just plot this one. The step response for this one. Now what we have, comma 4. So we have to realize this system. We have the sys transfer function and then we have s plus 4 minus s plus 4. So 4a square minus s square. So this is 16 minus 1, comma. Let us say we have 1. Okay, 16 s square minus 16. Is equal to 3f minus s plus 4, comma s plus 3. And this has to be multiplied with another transfer function. Minus 4 minus 1, comma minus 2, comma 12. So we have sys into sys 1. This is the overall transfer function. And what do we need to see? We need to check this step response of the system. We are expecting, since there is a right half plane 0, we are expecting a undershoot. So you can see from 0, it is moving towards negative, and then again it is going to a positive. And as we found out, the angle, like magnitude, is 32. Steady state magnitude that we found out. Okay. Let us this one. 1.68, 1.8193, 0.2, Amplitude is minus 1.1, and then it is increasing on both sides. So from minus 1.1, when we are going this side, it is increasing, and then again here also it is increasing. So minus 1.1 is the minimum. So what is the undershoot that we get is minus 1. It's basically 1.1, because from 0 we are calculating. So magnitude is 1.1. Let's erase this. So this we have found out. This is 1.1. Now this is a border plot. We can say this is the magnitude plot and it's 0 dB. So for all frequency it's 0 dB. That means gain is 1. And if you see the phase, it is changing from 360 degree to 180 degree. So delay is approximately minus 180 degree. Okay. So what can we say about this one? Obviously, since this is having magnitude as 1, so its transfer function should be like this, so that these two in magnitude will give 1 after cancelling out. And since there is a delay, which is because for this system, what delay we expect at omega tending to infinity. So if it is a minimum phase system, so this would give minus 90 number of poles minus number of zeros. Now same number of poles because it is strictly proper transfer function. So we have this as 0 degree. Yes. Sorry. So that means if it is a minimum phase, it should have phase angle which is 0 degree. But here we are seeing that phase angle is changing from 360 degree to 180 degree. So minus 180 degree delay. So that means this is a non-minimum phase system. Is for minimum phase system. So that means this border plot represents a non-minimum phase system. And since the gain is 1 at all frequencies, so this is a all pass filter. Okay. So these are the questions related to week 10 content. I hope you have no doubt in questions. So we'll conclude the session now.